last time, which was literally the last thing that we did, as we said, logarithms are inverses to exponentials. So let's graph some exponentials. And so we did. So this red graph is something like 5 to the x. Its graph would look something like that. Anything bigger than 1 raised to the x. The purple graph there is, I don't know, like 2 thirds to the x. Its graph will look something like that. If you take anything less than 1 and exponentiate that, then you'll get exponential decay instead of growth. Both of those are one-to-one functions. 1 to the x isn't. Logs are those inverse functions. The inverse of like 5 to the x, log base 5x, its graph will look like that. Log base 2 thirds of x, its graph will look something like that. So that's where we left off. We noticed that if b is 1, 1 to the x isn't a one-to-one function, so log base 1 of x isn't a function at all. It violates the vertical line test. Let's read off some things from this, though. Those are the graphs of the logarithmic functions. Only the red and purple ones are actual functions. What are the domains of those functions?
They would both be 0. Yeah, 0. Yeah.
Cool. Yeah, there's even a vertical asymptote at 0, so you can see that it's probably not included. And then anything bigger than 0 looks like it's in the domain. What about the range? What y? Nice. Everything. And that agrees, right? This range should be the same as the domain there. Yeah, you can put anything into an exponential. This domain should be the range there. Exponentials are positive, that's why the domain is only positive things. Feel good? Yeah.
So is the graph on the second one, the log, is it like flipped? Because of the point is it says 0, 1.
Oh yeah, absolutely, that's wrong, isn't it? And it's wrong here too. This one should be 0, 1.
Yeah.
This one better be 1, 0.
That's confused.
No, yeah. Apparently I was confused. So let's read off some more things from this graph. There, now it won't do that. Lose focus. Tell me about the x-intercept of the graph of the logarithm of x.
1.
Yeah, maybe I'll be a pedant and say either x equals 1 or 1, 0. Tell me about its vertical asymptote.
It has a vertical asymptote at 0.
Yeah. And again, I'll be a bit of a pedant. I'll say x equals 0. Tell me about its horizontal asymptotes.
It doesn't have it.
I guess like grammatically that's nonsensical. It doesn't have any horizontal asymptotes. Nice. So the next thing I want to focus on is building on this stuff about domain of logarithms. So that means whenever you see a function that involves a log, the stuff inside the log must be positive in order for the function to make sense. So let's try to use that. So, as on that previous page, the domain of log is 0 to infinity. So, specify it as an inequality if you want x bigger than 0. If you want the domain of log of some stuff, what do you need to do? You need to solve, let's put quotes around it, a function to indicate it's the same function, strictly bigger than 0. So whenever you want to find the domain of something that involves a logarithm, figure out where that stuff is positive. That seems reasonable. Let's try to do that with just some examples. There are like 4 things here. I think I'll talk through one, and then I'll let you all pick which ones we do next. So if I want to find the domain of log base 2 of 3x minus 4, what inequality do I need to solve?
3x minus 4 is greater than 0.
Yeah. Anyway, like, this type of problem can get as complicated as any solve an inequality problem gets. That look like an easy one to solve? In fact, how many people have done already? Cool. What's the solution to that inequality?
4/3 magnitude. Oh, sorry, to infinity, and then including 4/3 because it has to be greater than 0.
Cool. Nice. I didn't actually do any of the work to solve that inequality. Should I have? All right. So I see variety down here. Let's go through and we'll write down the inequalities we need to solve, and then we'll see what we want to do. If you want to find the domain of this, what inequality do you need to solve?
4 minus x squared. Greater than 0.
Nice. Just whatever is in the parentheses needs to be positive. If you want to find the domain of this next one, you need to solve 1 plus x over 1 minus x bigger than 0. For this one, you need to solve absolute value of x bigger than 0. And in looking at those, which ones would you all like to talk about? Let's try to prioritize which one people, well, yeah, which one? Yeah.
Oh, I always forget absolute value because it turns into the two equations. And I always kind of forget how to.
Yeah, we can talk to absolute value. I think this one's actually easier to do if you just try to draw a picture. So what does the graph of absolute x look like? Like a V, with that vortex being right at the origin. So that means that I want to know what x values result in absolute value of x being positive. Well, let's just go through and check. Do these x values result in absolute value being positive? Why not?
Because negative. Wait, which x values?
Which x values result in absolute value of x being positive? So x is like -3. What's the absolute value of -3?
3.
Is that positive?
Yeah.
So that's included.
Oh.
So like that point has absolute value of x bigger than 0. What if I pick a point over there? Does that have absolute value bigger than 0?
Yeah.
Is there any point that doesn't have absolute value of x bigger than 0?
0. All of them.
0 is bad, right?
Oh, 0.
Absolute value of 0 is 0. So the only thing not in the domain is x equals 0. And we can go through it algebraically now, but graphically it's nice. The only input with absolute value of x not bigger than 0 is x equals 0. So the domain is all numbers but 0. Which you could then put in interval notation if you wanted to. So there's one way to think through this one. Let's also just do this one like following the algorithm. Absolute value is like a slightly complicated function. So in order to solve an inequality, start by solving equality. So here's strategy 2. Let's start by solving absolute value of x equals 0. What are the numbers that have absolute value equal to 0? 0. And that's it, right? If it's negative, then the absolute value becomes positive, and so it's not 0 anymore. So now the game is like some sample points. If there's x equals 0, and I want to solve strictly bigger than 0, so I automatically know x equals 0 will be excluded. So I'll draw an open circle there to tell me it's excluded. What's an input less than 0?
One.
-1. What's the absolute value of -1? Does that satisfy the inequality?
Yeah.
Cool. So by testing -1, you get absolute value of x equals 1 is bigger than 0. So you include everything less than 0. What's something bigger than 0?
One.
Nice. So it looks like the domain here is -infinity to 0, together with 0 to infinity. Oh, but that agrees with that. Feel pretty good? Nice. So that's the one that's like, instead of being algebraically complicated, this is complicated because absolute value is sometimes complicated. Should we talk through one of the other ones? Which one? The one 4 minus x squared? The one with the fraction. Nice. So, I need to solve that inequality. And that's like a rational function. So there's like an extra step 1. So what are the first two things I need to do if I want to solve that inequality? Cool, go rid of the denominator, because the only way it's going to be equal to 0 is if like the top is 0, right?
Oh, yeah.
So maybe I'll write out those steps. So step 1, solve 1 plus x over 1 minus x equals 0, which just means 1 plus x equals 0.
Yeah.
So what x value does that give you?
-1.
-1. I think I'll have enough space to put my number line down here. And let's decide whether that endpoint will be included or excluded in advance. So that corresponds to when the thing is equal to 0. Will I include or exclude that?
Exclude.
Exclude, strict inequality. So I'll draw an open circle there just to tell me that it should be excluded already. What else do you need to do because this is a rational function?
Find where it doesn't equal anything. So
Yeah.
for asymptote.
Yeah, figure out where something bad happens, like where you wind up dividing by 0. Find the vertical asymptotes. 1b. How do you find the vertical asymptotes of this?
Domain is when it equals 0.
Yeah. When is that equal to 0?
X equals 1.
Cool. So there's x equals 1. Will that be included or excluded?
X.
Cool. Yeah.
It's asymptote.
Vertical asymptotes will always be excluded. All right, so it looks like there are 2 endpoints, so I need to check 3 sample points. I think we can break this up and do this in parallel. Or maybe just I don't want to do it myself. So I need a sample point less than -1, between -1 and 1, and a sample point bigger than 1. So pick a sample point in one of those regions and tell me what should be included or excluded. How people do that. Pull this up. All right, let's hear it.
So to the left of -1, it would be excluded, so negative.
Cool. It's like you test x equals -2 or -3 or something. All right. How about between?
Got 0.
Yeah.
Plugged in x equals 0, got something that was positive. I guess you probably got 1. Cool. That's one computation that I can actually do. Let's include that. What about something bigger than 1?
It's excluded because it comes out -2.
Groovy. Nice. So I didn't do any of the walk there. Does anyone want me to actually do, like, write anything down? All right. So let's see if that holds up. You can also read off the domain by graphing. So I'll have a computer graph this same function. So there's the graph. It looks like it's got its domain, like, starts somewhere and ends somewhere. Its domain is bounded. Let's see if it's bounded by what we think. So what we found was that x equals -1 gives some of the bounding, and x equals 1 gives some other bounding. Let's make those dashed. Not that the, like, making them dashed is super important, but it's nice to see it that way. That seem right? Does this domain look like it's all x values between -1 and 1? Excluded? Groovy. Nice. So, last thing I want to do in this is let's just remember that there's nothing that's going to be like new or fancy in what I'm about to do. Let's just remember some stuff about transformations. Let's sketch the graph of the natural log of 2x plus 1 minus 1. And I've provided here the graph of ln of x. You know what it should look like. It should look something like that. I've decorated some points that are like the easy points you can tell. Maybe I'll even draw in dashes this vertical asymptote at x equals 0. So let's try to just remember what transformations do. So I see this function, I see a 2 next to the x, I see a plus 1 and I see a minus 1. What order am I supposed to deal with those symbols in?
The x first, the 2x.
Last.
Oh.
So if the 2 were in front of the function, it would be first.
Okay. So then should we do like the shifting transformation first?
Let's do the shifting first. So if you shift this, I think I'll shift in this same picture. Let's just draw where everything goes. So if you go left 1, down 1. That vertical asymptote is a vertical line. If you shift that left 1 and down 1, where does it go?
Zero, -1. Which one? Oh, yeah. What are we talking about?
You've answered a relevant question. You told me where this point goes. I want to know where the vertical asymptote goes. Well, going down like won't do anything. If you take a vertical line and push it down, it's the same vertical line.
X equals -1.
Just x equals -1. Nice. So I'm going to see this vertical asymptote. It's going to come along and get to that point. E comma 1, when I go left 1, down 1, will be, I guess, E minus 1, comma 0. E minus 1 being like 1.7-ish, I guess. All right, cool. So that is ln of x plus 1 minus 1. All right, what should I do next? What does the 2 next to the x do?
Isn't it dividing all x values by 2?
Nice, yeah. All right, so it's a thing in the parentheses, so it does the exact opposite of what you would like expect. So divide all the x values by 2. Where's the vertical asymptote going to go?
negative 1 half.
And that's like a really bad looking negative 1. X equals negative 1. Alright, so x equals negative 1 half. Let's extend that x-axis so it goes far enough. That point there at 0, negative 1, where will it go? Stay put. Y-intercept doesn't change when you do this. E minus 1, comma 0.
E minus 1 divided by 2.
Cool. And if you wanted a decimal approximation, you could like use a calculator to get it. Or you could just like do the walk. E is 2.7-ish, subtract 1 is 1.7-ish, divide by 2 is like 0.65-ish? Ish. 0.85? Okay, I screwed up the division. Or the subtraction. I screwed up something. Nice. That feel pretty good though? Nice. Alright. So, with that done, the next thing I want to start in on today are the so-called logarithm laws. So these are the algebraic rules that logarithms follow. And in this particular packet, I won't like try to explain why these rules are true. The reason that they're true is because of facts about exponential laws, so we'll just take like the inverse of those facts. There is an extra credit in which you will go through the details. So let's try to walk out some of them. And some of them you already know. What's the log base b of 1?
1.
Nope.
No, 0.
0. What's the log base b of b?
1.
1. And in order to motivate these next couple, let's remember some facts about exponentials. So how could you rewrite exponential raised to the power x plus y? What's an exponential law that's relevant there?
You just add, is it you add x and y?
Right now I am adding x and y,
Oh, okay.
but in the
Oh,
exponent.
It's the log base b of x plus log base b of y.
Yeah, so you're answering the question that I'm not asking yet.
Yeah.
I'm trying to motivate why this should be true. So, logarithms take multiplication and demote it to addition. If you multiply inside of the parentheses, that's the same as adding outside of the parentheses. And why is that? It's because for exponentiation, if you add inside the parentheses, that's the same thing as multiplying the result. So, b to the x times b to the y is b to the x plus y. Logarithm does the exact opposite because it's the inverse function to this. If you multiply two numbers inside of a log, you'll add the logarithms. So if you like, this is saying that logarithms demote multiplication to like an analogous operation that's easier by 1. Addition's easier than multiplication, but it's like kind of like multiplication. What do you think division becomes?
Subtraction.
Subtraction. It better if like division is anti-multiplication, well, subtraction is anti-addition. And maybe I'll pause here and tell you like an application of this fact that was way more relevant like 40 years ago. So addition's easy. Like you can do addition easily. Even if you don't have a computer and like you want to add some like really big complicated numbers together, you can do it like, by hand. There's also a mechanical aid called a slide rule that is less relevant now than it was in the past. I know people here have actually seen a slide rule. Yeah, it's been interesting tracking how that number has been going down over my teaching career. So have you actually used one? Oh, okay. Right, so the whole point of a slide rule is you can add numbers together purely mechanically by just sliding something along the right distance. You start at like an input value, you slide it by the right distance, now it tells you what addition is. Because that's what addition means, like you travel to the right. So if you want to now multiply two big numbers together, here's what you can do. You get yourself a book of logarithm values, because these books used to be relevant. You would have a book that's just giant table of the log of this number is that number. So you'd go there, you'd say, oh, okay, the log of this number is that, log of that number is that. Now I need to add those two numbers together. So I'll add those two numbers together. Now I know what the log of the product is. Well, now I just need to go backwards. So I'll grab this other inverse log table, also known as exponential table, and I'll see what multiplication should be because I know what the log should be. And hey, you've just done multiplication without doing multiplication. That's a less relevant thing now. But still, if you're in a situation where you'd rather think about addition than multiplication, you can by taking a log. Or subtraction instead of division. And the last one to think about is exponentiation. So multiplication gets demoted to addition. Division gets demoted to subtraction. Let's just follow that pattern. What should exponentiation get demoted to? I think multiplication. So the log of x raised to the y is the log of x multiplied by just y. Notice the y doesn't have a log around it.
And wouldn't that be the same if it was in front of the log? You do like y log x, wouldn't that be the same like notation?
Yeah, multiplication is commutative.
Yeah.
So it doesn't matter what order you multiply in. That feel pretty good? So there are just some facts. We'll use them for things. There's also this change of base law that we talked about. Let's just write it down again. I wrote it down pretty informally last time, but let's see how many people just remember it. If I want to write log base, let's suppose you want to write log base 5 of 23 down. How would you do that in terms of like base 10?
Log 23 divided by log 5.
Yeah. And I guess you didn't specify, but you meant base 10 because I wanted base 10. The point is though, like the base you use in that fraction doesn't matter. You could pick your favorite base. It could be ln, could be log base 10, could be log base 2. The log base a of x for any choice of a, any legal base a, and any number x is the log of x with respect to whatever base you want, divided by log base b of a. And you get to pick that base however you want. There's a similar rule for exponentials, and maybe this seems believable. We've seen the graph of every exponential function. They all look basically the same, right? They all like grow like this, unless the base is less than 1, in which case they decay instead. As a result, all exponentials are kind of the same, and logarithms let you see exactly how they're the same. A to the x is the same thing as any base b raised to the x times log base b of a. So there's only one base for an exponent. It can be whatever base you want. If you're doing calculus, it should be base e, because everything works better on calculus if you walk base e. If you have a calculator that's happier to do base 10, then maybe those bases should be 10. All right, so here's what we're going to use these laws to do. These laws will let us simplify expressions involving logs to things that are easier to work with. And here's the most obvious one. We'll do one or both of these, depending on what people want. I think maybe what I'll do is I do one, then you do one. So let's take a look at those two expressions. Log base 3 of 2 plus log base 3 of 1.5. So on the one hand, I could bust out a calculator, compute log base 3 of 2 and log base 3 of 1.5, add them together, and I'd get a number. There would be whatever rounding error the calculator has built in, so maybe you wouldn't trust like 100% the answer. But if it's a reasonable number, you'll probably like see what it is. Let's do instead of doing that though, while I was stalling, how many people did exactly that? What'd you get?
Log base 3, or like, what the end?
Yeah, so I guess 1 is what you, yeah. So let's do that in this case. So apparently this quantity should just be 1, let's see if we can get it to that. So this will be the whole log base 3 of 2 plus log base 3 of 1.5. So I see two logs being added together. That logarithm law says that I could write that as a single log with multiplication on the inside. And 2 times 1.5 isn't that bad to multiply together, so I think it would improve our life to write that as a single log. Equals log base 3 of 2 multiplied by 1.5. What's 2 times 1.5?
3.
3. So I have log base 3 of 3, which is?
1.
Cool. Do you think you could do something similar to compute the gold underlined one?
And also equal 1.
I don't know, I didn't do it.
Oh, I'm just saying, just based on.
I suspect you're sitting next to someone else who did. Did you get one?
Right, did you get one?
Okay. So far I hear 2 votes for the answer as 1. Do I hear a second? Cool. Do I hear a call that, well, I see people just like walking along, so. People want me to do any walk on that one? Neato. Yeah, you wind up with like log base 5 of 5, which is known to be 1. Cool. So those 2 examples were like obviously very carefully curated so that the thing you get when you multiply them together is like a power of the base, because that's basically the only time when I can do a logarithm computation directly. Let's see this used to do algebra instead. So I claim that this is an equation that we can solve. Log base 3 of x plus log base 3 of x plus 8 equals 2. And you know, before we even do that, could we like, let's cheat fast and see what the answer should be. How could you like figure out what this answer should be without doing any algebra if you have like a graph?
Or look at the x value that equals to 2.
Yeah, you want to like, if you want to graph that, you want to know when is the y value 2. So let's just graph it. See when the y value is 2. And there is like a reason I'm doing this. We're going to get something interesting when we do the algebra. Log base 3 of x plus log base 3 of x plus 8. And it would be useful to like have you do the graphing too, just to like, but it takes like an extra minute to do it on like a handheld calculator, and some of you don't have one on you, I think. So there's a graph. I want to know when is y equals 2, so let's also graph y equals 2. Let's zoom out to make sure we're not missing anything. How many solutions does it look like there are? Just the one. And coincidentally, what does that solution look like it is?
1.
X equals 1 again. So by looking at a graph, I'm off the page. Graphing x equals 1 seems to be the answer. Let's do this algebraically too. So here's the thing that like you look at this equation and it's annoying. I see 2 different logs on the left-hand side. If there were just one log, I could rewrite an exponential form, get rid of the logs. That would improve my life. But there are 2 logs, so it's not really in logarithmic form right now. Could I rewrite the left-hand side so there is only 1 log? Yeah, do it. Cool. What's inside those parentheses?
X squared plus 8x.
Cool, because it should be x times x plus 8. So I think the distribution's useful. Let's do that. What's on the other side of the equal sign right now? 2. Right, we didn't do anything on that side, so just hold on to it. All right, so the whole point of that step is now I see something that I can put into exponential form. What's the base? Raised to the power. And then it's the stuff inside the log. Equal sign matters. All right, does that look like an easier equation than we started with? That's progress. That look like an equation that you even just know how to solve? Should I do any more algebra from here? Okay. Then I am going to just be quiet for a second. Dot, dot, dot. And you'll tell me what x value you wind up with.
X equals -9 over 1, but then the -9 obviously doesn't equal 2, so it leads to x equals 1.
Nice. Tell me why -9 was bad again?
Because it doesn't equal 2, or the value that we want.
Yeah, so let's check that. Let's see why -9 doesn't work. So the algebra tells us that -9 should be an answer.
Oh,
But, like, graphically, we know it isn't. Let's try to figure out the reason for this discrepancy. So, well, maybe before I move on, do people agree that that's what, like, the quadratic formula or factoring or something gives you? How many people quadratic formulaed? How many people factored? Completed the square? How many people didn't do anything and just waited for me to go write down an answer? Okay, do you want to talk through it at all?
No, I figured it out now.
Oh, okay, awesome. So let's try to plug in -9 and see what we get. So if we go up here, go back and, yeah, this space is fine. Let's test x equals -9, and we'll see what happens. We'll end up with the log base 3 of -9 plus the log base 3 of -9 plus 8. Is there anything, like, bad about that?
Oh, negative, yeah.
Yeah, so that's a negative inside of a log. And -9 plus 8 is also negative. I see 2 negatives inside of logarithms, that's bad. That expression doesn't make sense. So this is, so remember how, like, earlier in the semester I said you always check domain before simplifying? This is why. If you take this expression and simplify it using that log law by multiplying together, well, the thing that was really in there was like x times x plus 8. So you wind up with -9 times -1, which is positive. So you make the domain bigger sometimes when you simplify. That's what happened here. So here is the payoff, the cautionary note. And I'm going to put it over here, I think it's just fine. Check domain after solving a logarithmic expression. Yeah.
So, dude, let's say instead of like, we had like log 3 base x to the 5th, we still have one answer. It was equal to something, it would just be one answer.
Sometimes it'll be 1, sometimes it'll be 2. You could have as many solutions as you want.
Okay.
It happened that this equation had only one solution, even though the algebra kind of told us there should be 2.
I was also gonna ask, like, if we tested -9 and we saw that it wasn't like an answer, that means automatically we wouldn't have to test x equals 1 because we know that one's the answer. Would that be
Some equations have no solutions.
okay?
So I wouldn't even say you have to plug in x equals -9 and see if it solves the equation. Just think about, is -9 in the domain? And I see here just an x inside of a parentheses. That means x has to be positive. I see an x plus 8 in the parentheses. That means x has to be bigger than -8. And both of those have to be true. And the strongest one of the two is just x has to be positive. -9's not positive. So You can just check the domain. But now that we've checked the domain, is 1 positive? Is 1 plus 8 positive? So we're fine. Neato. That feel good? Let's talk through this next one. Well, let's see what people want. And I think the way we'll decide which ones we do is, do we think they look easy or we think they look worthwhile? I'm also down to just 8 minutes, so. Should we talk through the next one? Okay, let's talk through the next one. And maybe I'll even start the same way. Let's start by graphing. Log base 2 of x plus 2.
Is it always left to right with dividing? So x plus, like the first logarithm would always be over the second logarithm?
Yeah, the thing that is being subtracted from will be the thing in the top of the division symbol. But like if you saw instead negative log x plus log y, that would be log of y divided by x. So it's not like left or right that matters, it's which one has the minus sign that matters. Whichever one has the minus sign becomes the thing in the denominator. So let's graph this. Log 2 of x plus 2, x plus 2, x plus 2, okay, caps lock is finally off, minus log base 2 of x plus 1, and I would like to know when y is equal to 3. All right, so same question. How many solutions does it look like there are? Just one? And it looks like that solution is around negative 8.57. So the graph's not giving us an exact value. That's probably not exact anyway. Let's see if we can solve this then. So, first thing I see is there's this subtraction. You've already told me this should become division, right? So this will become log base 2 of x plus 2 divide by x plus 1. All right, what next?
Undo the log, so it'd be x plus 2 over x plus 1 equals 2 to their power.
Nice. And 2 to the 3 is something that you know. What is 2 to the 3?
8.
Nice. And I'm going to write down something cautionary because an easy mistake to make here. If you like accidentally think too quick, maybe you're a touch dyslexic, that's an easy mistake to make. So it's a thing to be careful about. It's a failure point to be aware of. If you get an answer, you check the answer, you see it's wrong, see if you did that. Because I know that's something I will make that mistake at some point during a lecture. Not intentionally, it just will happen. All right, cool. Does that look like an equation that is not too difficult to solve? Yeah, at a minimum, it looks better than it used to. What should you do next if you want to solve it? Cross multiply. X plus 2 equals 8 times x plus 1. And I'm painting myself into a corner space-wise. So I think I just want to be quiet for a second and you'll tell me what the x value is. Probably as a fraction, I guess.
I got negative 6 over 7,
Yeah.
I've had some calls for negative 6/7. Anyone actually want me to talk through doing the algebra at that stage that I didn't want to do? Cool. And maybe just to see if this agrees with the graph, because we have a Desmos graph right there. It says that should be the x value. We could do the division, get the decimals of 6/7. How about if I just do that? Does that seem to line up with that x coordinate well enough? Nice. So use the graph to check. And this last one, in 3 minutes, I don't have time to solve it, but let's reduce it down to a single log and then get rid of the log and then we'll call it good. So, let's see what I see here. I see a 2 in front of a log, and I see a minus sign between the logs. So what should I do?
Could you just divide by two from both sides?
Oh, you could divide the 2 to the other side, but then you wind up needing to divide this by 2.
No.
Because not everything on the left-hand side is multiplied by 2.
Okay.
What else could I do with that 2?
Distribute inside the parentheses, is that what you do?
Kind of. It doesn't literally distribute, but I see a log times a number. I could move that number inside of the log to make it an exponent, which isn't the same as distributing, but it's like
Yeah.
spiritually like that. So let's do that. I'll see log base 5 of x plus 1 squared minus log base 5 of x minus 1. Now I just see a log minus a log. So what does that become? Division. So I guess here's the shorthand. If you see like a bunch of linear combinations, so like numbers times logged, added and subtracted together, move all the numbers on the inside to make them exponents, and then divide and multiply all the stuff together inside the logs. I guess I need the other side of the equation equals 2 log base 5 x plus 1 squared over x minus 1 equals 2. So, can I get rid of the log now?
Yeah.
Cool.
85 to the second power.
Also known as 25. And I won't solve it, but maybe I'll just point this out. Does that look like something that's now an easier looking equation to solve than we started with? Does it look like something you in fact could solve if you had 5 minutes instead of 40 seconds? Yeah. And let's just make note of this. That looks like there's going to be like a degree 2 polynomial that you'll eventually get. So you expect 2 solutions to that thing. Do you think both of those solutions will solve the original thing? Maybe. You need to check.
Yeah.
So check domain when you're done. They might both actually be solutions. I might be overstating like what the quadratic polynomial is going to give you. Maybe this has no real solutions. Oh, so what do you think? Like, this could conceivably have imaginary solutions, right?
Yeah,
Have we tried to make sense of what it means to put an imaginary number into a log?
I don't think so.
We certainly have not. There is a way to make sense of it. You wind up having to think about topics in like complex variables to figure out what it should mean. It's not necessarily hard, it's just not something we do. Groovy. So, let's see. The open-ended homework I've posted for today is inspired by this like final example in the notes which we didn't make it to. So, I'm gonna go and push that deadline back. It's gonna be as if it's assigned next week instead of this week. Next week being the week after spring break. So that deadline will be pushed back, but there's no law saying you can't take a look at this problem right now. Nice. So I'm done now. If any of you like want to ask comments about this problem that's written down right now, you're certainly welcome to. Wait.
2 to the x equals 5.
2 to the x is equal. There's no equal sign there. That's just 2 things multiplied together. 1 equals.
That's what you think, that's good.
I don't.
I'm glad you showed up. I'll see you next Monday.
I see this light ruler thing and how it works. I want one had to work for one system to work on how to analog targeting. So it's all gears.
Oh wow!
You turn the dial to get your range and, you know, to calculate it.
And it's all like super mechanical.
Yeah. It's not that they're real accurate, but they kind of.
Yeah, like those like real old like handheld mechanical calculators are like bizarre things.
Well, I was concerned about, I could have to work in 5 extra.
Oh,
fires done to it, and that's World War II finish,
Uh-huh.
tile.
Uh-huh.
Yeah, I was like that. Nowadays, you kind of know what's up for the
Yep.
roofs.
Uh-huh. Ooh, let's stop the recording.